So that's another typical translation example. The two wheels of the vehicle are connected by a 20-kilogram link AB, which is this, with center of mass slightly offset from the center of the wheel. It's here, closer to B. And this connecting link, or sometimes it's called the coupler, has a pin connection with the wheel at B. And here we have a slot which is smooth at A. And as you might guess, if two were pin connections, we would have four unknowns, okay? Two perpendicular components for two reaction forces. But since we could write only three equations, it would be an indeterminate problem. That's why it's like a fixed and a roller support, okay? If the vehicle has a constant speed of 4 meters per second to the left, determine the magnitude of the force that's supported by the spin when that angle is 30 degrees. Here, actually, there are a few interesting things we might discuss. We may analyze the motion of this link as an absolute motion. That is, we may use a coordinate system that's fixed to the ground, but we could as well use a coordinate system that's fixed to the vehicle. The reason is vehicle is not accelerated, therefore it is an inertial reference frame as well. So whether the vehicle is traveling to the left with this speed or not will not change the force at B, okay? Even if it were stationary, say the wheels are suspended or it's on a lift, but the wheels make the same speed like the vehicle is traveling to the left by 4 meters per second, does not change anything because the vehicle is an inertial reference frame. If we assume Earth fixed reference frame is inertial, okay? So whichever you prefer is okay. But if the vehicle were accelerated, then we had to analyze the motion with respect to an inertial reference frame. And let's see how this connecting rod moves from a rather old movie by Buster Keaton. You see, that's another connecting rod. And the locomotive travels to the right, or if you like, it may travel to the left. As you see, the connecting rod is always parallel to the ground, and the man could sit on it, although it's quite dangerous. So it's in translation, okay? Its angular position does not change. Therefore, it does not have an angular velocity nor acceleration. So if we return back to our problem, well, for the wheel, I can compute the angular speed either by this approach where the contact point is the instant center of zero velocity and the distance between the instant center of zero velocity and the pin is the radius. So the vehicle was traveling by 4 meters per second and the radius of the wheel was 0.6 meters. So the angular speed of the wheel is 6.67 radians per second. Since the vehicle is traveling to the left, okay, and this is the instant center, the wheel should rotate counterclockwise. So this is what we get. And since AO is 0, which is the also acceleration of the vehicle, therefore, actually what we say was the velocity is constant. Uh, well, if you like, we may use NT coordinates or R theta coordinates to analyze motion of point B or A, which are actually identical, but using Cartesian coordinates is equally well simple. So what I'm going to use is Cartesian, but you might also use NT or R theta, the polar coordinates. Remember, in polar coordinates, since point B makes fixed axis rotation about O, R dot and R double dot would be 0, so they would yield identical results. The only difference is N is negative of R. So actually, if you like, you may start with NT coordinates, which I did so. So I have calculated the tangential and the normal accelerations of point A. Actually, it's the same for B. It doesn't matter. So although I say A, it's B, and also it's for G, okay? If a body is in translation, every point on it would have the same linear acceleration because there is no rotation. And here, omega and alpha are dead of the wheel, okay? Since the vehicle is traveling with constant speed, actually the wheel speed is constant and the acceleration of the wheels would be 0. So I will have no tangential acceleration for the pins, but because they are on circular paths, that's the normal acceleration. And as you see, it is quite large, nearly 2g, okay, twice the gravitational acceleration constant. And it is towards the center. Now, I know theta, it is 30 degrees. So after obtaining this acceleration, I can convert it into Cartesian components where x is horizontal, y is vertical. And as you see, this is the normal direction for theta equals 30 degrees. So this times cosine 30 would be y acceleration downwards, which is this. And the same thing, 17.78 times sine 30 is the x acceleration, again, negative. Okay. And then I will continue working in Cartesian coordinates. But if you like, you can just split A into NT and put B and BT as well. If you like, you would get the same answer, okay? So what I will be doing is I'll sum up the X forces equated to MAX, sum up the Y forces equated to MAY, and normally what we do is we take moment of the forces about G and equate it to IG alpha, where alpha would be 0. But here what I did was I just took moment about this point and equate it to IG alpha, where alpha is 0, so the first term is 0, and moment of MAG about this point, okay? So this is what I did, but you could use this as well if you like. They're equally well. Now, if I sum up the horizontal forces, the only unknown is Bx. So I have Bx. Actually, here you might see that I have my free body diagram and also the kinetic diagram is on it. That's not something actually very good because the forces, they should be on the left-hand side of the equation. The acceleration should be on the right-hand side. So it would be better if you draw two figures so that you won't get confused. But because my slide is small and I had to do quite many computations to fit everything in, I just did this. Do what I'm saying, don't do what I'm doing on this slide, okay, while you're solving the problem. Or as the good old Turkish saying says, hocanın dediğini yap, yaptığını yapma, okay? Because I know how to solve it. That won't be a trouble for me, but I strongly recommend you to draw the kinetic diagram separately. So what I have is the only x forces. Bx is equal to the acceleration in x direction times the mass. So I can solve Bx very easily. That's good. But when I sum up the vertical forces, I have Ay upwards, positive direction, By downwards, so negative direction. And then I have the weight, mg, is equal to mass times the y acceleration. And I get a relation between Ay and By, but can't solve them individually. So I have this. Now, if I also write this expression, I'm going to get another relation, moment of Ay, moment of By, and what else do I have? This doesn't have any moment. I'm taking moment about G, so mg has no moment, is equal to 0. So by using this relation and that relation, I could solve Ay and By. But if I take moment about A, I will eliminate this unknown and I could solve directly By. And then if I need Ay, I can substitute it here. So it's up to you. Both would yield the same answer. So what I'm doing is if I take moment about A, this is 1.8 meters times By, and actually it is clockwise, and I'm taking clockwise moments positive. Why? Because I will take also moment of MA and I'll say clockwise is positive, but if you like, you could put a minus sign in the front to say counterclockwise is positive. You have to take counterclockwise positive if you take cross products. But here I'm taking ordinary moments. I'm not using vector cross product, so it's up to you which direction you choose positive, and I chose clockwise positive, and I did consistently, okay? So this is 1.8 By clockwise positive. Mg, and this distance was 1, again it's clockwise positive, is equal to, I will take vertical component of MAN, which is this. I'm sorry, this is MAN, that's true. So that's AN, this is MG was here, again clockwise, so it's positive. So what I get is By, and as you see, By, I assumed downwards, turns out to be positive, okay? And if I square this and square that and sum and take the square root, I'll get B, which is the reaction on pin B. And if you like, you could also substitute this into here to get AY as well, which is not asked. Okay? Any questions on this problem?
Hocam Why don't we have any x component for a?
Well, you have a slot here, which is smooth, okay? So it's something like this, and this is the pin. So it's capable of moving horizontally. Am I right?
Okay.
So there is no restriction, there's no reaction force. But for B, what happens? You have a pin and there's a hole, so you can't move it horizontally. You have an X reaction. You can't move it vertically. You have a Y reaction. Those reactions are restricting those, but rotation is permitted. Therefore, there is no moment here, assuming it's
Okay.
frictionless.
Thank you,
Okay,
hocam.
sure. Any other questions before we proceed? So translation is rather simple, but we have to be careful. Uh, there is the acceleration of the mass center, which we have to consider in force equations. If we take moment about the mass center, no trouble, it's equal to zero. But if you would like to take moment about a point other than the mass center, this term is zero, but still you have to take the moment of the mass center about the point you take moment, okay? This is the difference from statics. Okay, then we may discuss fixed axis rotation. Now, in fixed axis rotation, all points on the body follow circular paths centered at the rotation axis. The same is true for the mass center. Uh, well, let's not consider this omega. Let's assume everything is counterclockwise. If it's clockwise, then omega is negative. So disregard this omega, or in the book, assume this is positive, alpha is positive, and the mass center is going to have a tangential acceleration, which is r, that's the distance of mass center from the rotation axis, r alpha, and a normal acceleration, r omega square. We have the force equation, sigma F, the external forces on the body, including the reaction forces at the rotation axis, is equal to mass times the acceleration of mass center. And for fixed axis rotation, the best coordinate system is not Cartesian, but normal, tangential, or polar coordinates. And as I say, they yield identical results for circular motion. The book uses normal tangential coordinates, so we can split it into two equations. And you will take moment about the mass center, and it's going to become mass moment of inertia about the mass center times the angular acceleration. This is the regular equation, okay? So these two form the Euler's first law and the second law. But you might want to take moment about the rotation axis. And as we did the derivation, it's mass moment of inertia about the rotation axis times alpha. And to show that it's so, actually the general formula said it's Ig alpha plus the moment of MAG about the rotation axis, or about the point you use. So this is what we will have. As you see, the normal acceleration has no moment about the rotation axis because its line of action passes through it. So the tangential acceleration is alpha r, and we had another r, so it's r squared. And as you see, we have alpha common. So Ig plus mr squared, according to parallel axis theorem, is mass moment of inertia about the rotation axis. So that's why we have this formula. Now, this is one case. The other case is you may have G at O. That is, the body is rotating about its mass center. In that case, sum of the forces should be equal to zero, including the reaction forces. Actually, that type of a thing is then sometimes called, in terms of machine dynamics, unbalanced rotation. That is, the mass center is not here. So when this is rotating about O, you will have a shaking reaction force at the pin. And actually, it's like the vibration or silent mode of your phone. It's going to vibrate, okay? In machines, mostly, we don't like such things. So what we try to do is, for example, for the wheels of the cars, you try to bring this G to O so that you can drive the car smoothly and there won't be any shaking reactions at this point, which is the axis of the wheel. Okay? In that case, sum of the forces would be zero because if G is here, it has no acceleration. So things are quite simple if we know kinematics of the particles, kinematics of the rigid bodies, plus everything about the particles. So rigid body concept, the theory is simple, but in applications, we have to be careful. That's why I will devote some time to solve various problems. Any questions about the concept? Okay, then let's try a simple example. We have a narrow ring like this, which is pinned here, and it's in vertical plane. That is, we have gravity downwards. If we release this pin when this angle is zero, we would like to determine the two components of the reaction force at the pin in terms of theta. That is, actually, we would obtain general expressions for the reaction forces at this pin when theta continues to increase from zero. Okay, is the problem clear? So you have the ring, it's like this. Let me try to show it. You have a ring, you pin it from one of its sides, and it's like this initially, and you release it. So because of its weight, it goes down, and you would like to determine the reaction force at the pin. So what I have to do is, this is the original figure. I drove the free body diagram. What I have is weight acting at the mass center, and I have the tangential and normal components of the reaction force, and I have no guess about the directions of these forces. So what I do is I assume Fn is along positive n, Ft is along positive t. If I'm mistaken in any one of those, it will turn out to be a negative number, okay? And most probably, at least Ft would be negative. Why? Because it should be balancing mg. But I don't care, okay? So what I'll do is, Fn is equal to MAN, but this AN is actually the N component of the center of mass of the body, which is C for this problem, okay? So actually, these accelerations are normal and tangential accelerations of the mass center, okay? Although it's not stated explicitly, it is so. So actually, for point C, the normal acceleration is omega square r of the ring, and the tangential acceleration is alpha of the ring times r. Okay? And they're in positive direction. And if you like, you can take moment about this point, but we know for fixed axis rotation, you can take moment about rotation axis, and it's equal to mass moment of inertia about the rotation axis times alpha. So we could use this as well. Now, for the ring, the mass moment of inertia is not given, but remember the radius of gyration. If you had a distributed mass in a body, you can collect the same mass on a ring whose radius is equal to radius of gyration. So for such a thin ring where this thickness is negligible compared to the radius of the ring, Ig is mr square. Okay, so mr square is mass moment of inertia about c. By using parallel axis theorem, I will say plus m times the distance between the two axes, which is r square, I get IO. Okay? And actually, I will start with this expression. And what is interesting about this expression is these two unknown forces do not have a moment about O. Am I right? So I eliminate the two unknowns which are asked in the problem. But actually, this expression supplies me an important information. So what I have is, this is the only force which has a moment about point O. And if I assume counterclockwise rotation positive, moment of this force is negative, okay? So this distance up to here is r cosine theta, okay? So mgr cosine theta, it's negative because I assume alpha and omega to be positive counterclockwise, and actually we know it's going to accelerate in clockwise direction. That's why I have a minus sign. So I obtain an expression for the angular acceleration. Okay. I didn't get anything about those reaction forces which are asked, but I obtain an expression for the angular acceleration, which would be useful. Then I may move to these two equations. And for example, for tangential direction, I have this reaction force, which I wrote it as a function of theta, okay? And then I have t component of this plus mg cosine theta, that's all. These are the two t forces, is equal to m times alpha r. So actually, I have an expression for alpha, which I'm going to substitute here, times r. So this is one expression. For ft, then I can take this to that side and get the answer, which is negative m over 2 g cosine theta. Since m is positive, g is positive, you see the direction I assume is incorrect, but that's not a trouble, okay? You don't need to guess the correct directions of forces. You will just get a minus sign in the front, okay? That's not a trouble. Clear? So this is one of the answers. Now I would like to find also Fn where I will have a little trouble. What I want is Fn as a function of theta, and this mg is going to have an mg sine theta opposite to Fn. That's why I have a minus sign in the front, is equal to m omega square r. Now here the trouble is, okay, that's a function of theta, but here I have the angular speed. And actually we are given that angular speed is 0 when theta is 0 because it's released from rest there. So I have to compute what would be the angular speed for a given theta if it's released from rest when theta is equal to 0. Okay? And again, I'm going to use this alpha as a function of theta to compute omega. Okay? Remember, we had this expression, which was a differential expression, which is valid for all sorts of motion. And if I know alpha as a function of theta, I can directly substitute it and integrate this because the variables are already separated, okay? So I'm going to use this information and I will integrate that expression, okay? Released from rest to the current speed, omega d omega is theta starting from 0 to current theta, alpha d theta. And alpha was negative g over 2r cosine theta d theta, so it's integrable. Now, this is going to yield omega square over 2 in between these two limits. And when you integrate this, it's going to become g over r, 2r actually, sine theta, and we had a 2 here, so the 2's will cancel when integrated from 0 to theta. So that's omega as a function of theta. So I could substitute this thing into here to get Fn as a function of theta, which is 2mg sine theta. Okay? Any questions? Is everything clear? Definitely. Uh-huh. Exactly. There must be a moment to rotate it, okay? It's not the force. It's the moment of the force. Now, I got what you mean. Let me just make a sketch here to show you what it is. That's a very good question. Let me see. Suppose you have something like this. Okay, this is a body. This is the rotation axis. And it's also the mass center. Okay? And suppose you have a force here, which is an external force. Am I right? Now, what we have is sigma F is equal to m times AG. Am I right? What is AG if it's the rotation axis? It is 0. Am I right? So I should have sigma F equals 0. How come this occurs? Well, I have to draw the free body diagram. I have this external force, ignore that stupid horizontal line. I'm going to have an Fx here, or maybe let's say R so that it's not the same F, and an Ry here, okay? Now, what should happen is this force plus resultant of these reaction forces should be zero. Am I right? So actually, reaction of these two forces should be a force like this, which is same as the external force. Actually, they're all vectors. I'm sorry, I'm just doing quick things. So the couple of these two forces is this. Clear? So the sum of the forces should be equal to zero. And the best part is, because that is zero, if a body is rotating about its mass center, it's not going to shake its foundation like the vibration mode of your cell phone. It's like a well-balanced wheel of a car. Why do you balance the wheel of the car? To drive smoothly. If the wheel is like this, suppose, if this is your car's wheel, that's the axle, but that's the mass center that rotates about the axle. What's going to happen? When it's up, it's going to apply a force like this. When it's here, it's going to apply a force like that. When it's here, it's going to apply a force like that. When it's here, it's going to apply a force like that. So you will feel that the vehicle is shaking. Okay? Actually, there's another balancing. The car wheels are balanced in two planes. One is the external surface of the rim. The other one is internal surface of the rim. Although you bring the mass center at the center of the axle, if it's a single plane balancing, this is what I'm explaining in the figure, you may have a shaking moment, okay? Especially if it's in the front wheel, you will feel it in the steering wheel at higher speeds, and it's speed square dependent, okay? Those centripetal accelerations are omega square r, so at low speeds, they would be small, but as you increase your speed, the magnitude of that shaking force is going to increase with the square of the force, so you would feel really uncomfortable. And another thing, as you might know, we can't satisfy certain things exactly. For example, when you balance a wheel, you don't exactly bring the mass center to the center of rotation, but you bring it to close to it with a tolerance, with an acceptable tolerance. So if the balancing equipment is quite accurate, the distance between the mass center and the wheel center is, say, a fraction of a millimeter, which you would feel the shaking moment at speeds exceeding 200 kilometers per hour. But if it's an inaccurate equipment, say it's a few millimeters, then you might feel the unbalance at, say, speeds exceeding 100 or 120 kilometers. So you can't do anything exact, okay? You can't bring it exactly to that point. That's not possible in practical life as well. Okay, on computer simulations, you can enter the numbers exactly, but in real life, in every measurement, you have tolerances. So, anything else before we proceed with the general plane motion? Okay, let me just clear this so that we won't see the same things in the next lecture. Uh, let's continue with general plane motion, which is actually the final section of uh, direct application of force mass acceleration method. In that case, we have this expression, which is Euler's first law. We sum up all the external forces on the body and equate it to mass times acceleration of the mass center. We just split this equation into xy and t or r theta components to be able to do the necessary calculations. And actually, you might choose whichever coordinate system you think is appropriate. And actually, if you choose the correct coordinate system, I shouldn't say correct, appropriate coordinate system, the solution of these equations would be very simple. If you choose inappropriate one, well, still you can solve it. It would be a little longer. Then we have the moment equation. You can write it as a scalar equation because it's a plane motion. So you can assume counterclockwise, or if you like, clockwise moment is positive. Whatever moment you choose positive, alpha is in the same direction. I recommend you to choose counterclockwise, not to think every time. Okay, I did in the previous example clockwise positive, but I think it's a better practice if you automatically assume counterclockwise positive. You could use this, or sometimes you may take a moment about an arbitrary but specific point where you might eliminate some of the unknowns coming from here and write the expression like this and directly solve one of the unknowns. That's also possible. So what we do is, actually, that shouldn't be a vector because that's a scalar, okay, clockwise or counterclockwise. Ig alpha plus moment of mag about the point you take moment. So that's quite simple. What we have is actually we have to consider constraint and unconstrained motion. For unconstrained motion, the acceleration components, that is the two components of AG, either xy and t or r theta, and alpha are three independent quantities, okay? But if you have a constraint motion, then there would be one or two kinematic relations between the two components of these and the angular acceleration. And also, if you have constraint motion, there will be reaction forces because of the constraints to impose or to force the body to behave like this, okay? So we have to be careful whether the motion is constrained or unconstrained. So, for example, for this body, it's unconstrained. So whatever forces you apply, the resultant is going to tell which direction A is going to be, okay? And moment of those forces about the mass center is going to tell you what alpha is going to be. That's all. But if you have a constraint motion, you will also have reaction forces. And the sum of those forces, which are the external forces plus the reaction forces, will force A and alpha to obey the kinematic constraints. Okay, so I'm going to solve problems about those, we will see, but we should be very careful to identify whether it's a constraint or unconstrained motion. Okay, again, in constraint motion, you sum up the forces, but you also have the reaction forces. They would be equal to mass times the acceleration of the mass center. And when you take moment of the external plus the reaction forces, it would be equal to IG times alpha, okay? Now, another thing we have to be careful is when we choose a coordinate system, anything along the positive coordinates would be positive in the equation. Anything opposite to that would have a minus sign, okay? So we should be careful about those, okay? Any force that's along the positive coordinate direction is positive. Also, if you have action-reaction pairs, use them consistently, okay? If this is the action, reaction is collinear, it's equal and opposite direction. So that's all. We have to draw free body diagrams and do all of those. And I will start solving examples, but have just 3 minutes. So if you have any questions, I'll be glad to answer. If not, we can have an extended break of 13 minutes. We don't need to rush. We have enough time. I have lots of examples that I will discuss, but time is sufficient. Any questions? Okay, then let's have our break and be back at 9:40.